Every time you ask a generative AI model to draft an email or write a line of code or even just create an image, you are actually consuming roughly 10 times the electricity of a standard web search.
Which is just wild to think about.
Right, 10 times. Now, if you take that and multiply that single interaction by billions of users day in and day out, it adds up fast.
Oh, incredibly fast.
We often talk about the digital world as the cloud, like this weightless, invisible place where our data just floats around.
Yeah, but that cloud is very physical.
Exactly. It's crashing back down to Earth,
Yeah.
and it is completely starving for power. So, welcome to our deep dive today, where we are looking at an energy gold rush that is literally physically altering the American landscape.
And the scale of this resource reality, I mean, it is staggering.
Yeah.
Based on the Department of Energy reports we are analyzing today, the demands of artificial intelligence and machine learning are growing so rapidly that, well, data centers could consume up to 12% of total U.S. energy production by 2028.
Wait, 12% of the entire country's energy?
Yes. We are talking about a single sector swallowing more than 1/10 of the power generated by the entire nation.
That is insane. And the biggest tech companies in the world, like Microsoft, Amazon, Google, Meta, they're looking at that 12% figure, right? They're looking at the aging American power grid and realizing the math simply does not work.
It really doesn't.
So they are executing a massive structural pivot. They aren't just buying green energy credits anymore, to look good on paper. They are actively transforming themselves into nuclear energy developers.
Which is just a fundamental shift in corporate behavior. I mean, you have software and hardware companies basically taking on the heavy industrial burden of nuclear physics.
Yeah, becoming utility companies themselves, essentially. So our mission today is to figure out the mechanics of why this is happening. We've got a really dense stack of sources for this deep dive.
We do. We've got the Department of Energy reports, a highly detailed playbook from the Idaho National Laboratory.
INL, right?
Right, the INL playbook on nuclear data centers. And we're also looking at this whole recent wave of corporate energy acquisitions.
Right, so we are going to connect the dots across 4 structural pillars today. The speed to power gap, the relentless pursuit of what the industry calls 5 nines reliability, the strategic avoidance of grid politics, and this fascinating engineering breakthrough called direct thermal integration.
Which is super cool. But the foundation of all this, really that first pillar we need to examine, it's entirely about the concept of time.
Time. Okay, how so?
Well, the Idaho National Lab playbook refers to this as a cultural mismatch between the tech industry and the utility industry.
A cultural mismatch.
Yeah. I mean, think about it. If you are a hyperscale data center developer, your entire business model is measured in financial quarters.
Right. Move fast, break things.
Exactly. Your goal is to site, build, and commission a massive server campus in like 18 to 36 months, just to keep pace with AI advancements.
Because if you miss the wave, you're dead in the water.
Precisely.
Yeah.
But the utility companies providing the power, they operate in a completely different dimension.
Yeah.
Utilities don't think in quarters. They think in decades.
Right. Which makes sense for them.
It does. And that isn't because they are inherently inefficient or lazy. Their mandate is to provide stable, affordable power to everyone. So they are burdened with integrated resource planning, environmental siting reviews.
Rate cases, public hearings, all of that.
Exactly. The result is that if you want to connect a massive new tech facility to the public grid today, you are looking at a 5 to 10-year wait in the interconnection queue.
A 10-year wait. Wow. So to put this in perspective for you listening, it's basically like trying to build a state-of-the-art billion-dollar skyscraper in 18 months. You build it, it looks great, but then the city tells you the water main connection is going to take 7 years to install.
That's a great analogy.
So you just have a multi-billion-dollar glass tower sitting empty. But wait, if data centers only take 2 years to build and grid connections take up to a decade, aren't we just building incredibly expensive empty warehouses right now?
Well, that is precisely the crisis. The opportunity cost of missing the AI wave is existential for these tech giants. They absolutely cannot wait a decade for the grid to catch up.
Right.
That 18-month tech timeline just completely breaks the brain of a traditional utility provider. The institutional speed of utilities is designed for public prudence.
Meaning they have to be careful with the public's money.
Right. They cannot simply build a multi-million-dollar transmission line just because a tech company asks for one today. Because, well, if that tech company goes bust tomorrow, Everyday ratepayers are stuck footing the bill for that abandoned infrastructure.
Oh, right. My grandmother's electric bill goes up to pay for a dead tech startup. That makes sense.
Exactly. So the only logical solution for these tech giants is to abandon traditional grid expansion entirely. They just bring the power directly to the source, bypassing the queue completely.
Okay, which brings up an immediate question, because you're probably listening to this thinking, wait, didn't these companies just spend the last decade promising to go 100% green?
Oh, absolutely.
Yeah.
They all made those pledges.
Right, with wind and solar. So if they are building their own power sources now, why suddenly pivot to nuclear? Why not just build a massive solar farm next to the data center?
That is where we have to look at the specific nature of AI computation to answer that.
Yeah.
AI training is not like a standard manufacturing plant.
Okay.
A traditional factory, they might be able to slow down production if a storm rolls in and the wind turbines stop spinning. But training a large language model, that takes months of continuous uninterrupted processing.
Right, you can't just pause it.
No, you can't. If the power drops out even for a fraction of a moment, the data can corrupt and the entire training run has to be completely restarted.
And that brings us to the second pillar. The industry term in our sources for this is the 5 nines. They require 99.999% energy reliability.
Which is an incredibly high bar.
It equates to, what, about 5 minutes of allowable downtime per year?
Yeah, roughly 5 minutes a year. And the financial stakes for missing those 5 nines are just devastating. The Department of Energy estimates that downtime at a major AI data center can cost over $8 million a day.
$8 million for one day of being offline.
Right. This is why we need to clearly define the concept of baseload power here. Baseload is the absolute minimum level of electricity demand required over a 24-hour period.
It's the floor.
Exactly. It's a flat line. You need a power source that produces a constant, unwavering flat line of energy day and night, entirely regardless of weather.
And intermittent renewables like solar and wind just don't do that.
They don't. Even when paired with the absolute best utility-scale batteries we currently have, they simply cannot guarantee that massive baseload stability for months on end.
Yeah, I mean, you can't run a multi-billion-dollar AI training model and just, cross your fingers that the battery banks hold out through a 4-day winter blizzard.
Exactly. That explains why nuclear is stepping in as the perfect partner here. According to the DOE source, current nuclear plants operate at maximum capacity more consistently than literally any other energy source on the planet.
They just turn them on and let them run.
Right. They run for 18 to 24 months at a stretch without ever needing to stop.
Yeah.
And the advanced designs that are being funded right now, they aim to run for a decade without refueling.
A decade. That's incredible. And we are seeing this realization translate into massive capital investments right now. Just look at the corporate agreements detailed in our stack.
Oh, the deals are historic.
Let's actually run through these because the sheer scale is crazy. Microsoft is actively working with Constellation Energy to literally restart Unit 1 at 3 Mile Island.
Yeah, bringing it back online just to power their data centers.
Right. And Microsoft also signed the world's first commercial purchase agreement for fusion energy with a company called Helion, targeting 2028. And fusion, just a quick refresher for you listening, is the process that powers the sun. It's combining atoms rather than splitting them like traditional fission.
It is incredibly ambitious.
Yeah.
I mean, fusion has been 20 years away for the last 50 years.
Seriously. Then you look at Meta. They recently partnered with TerraPower to deploy up to 8 advanced nuclear reactors, targeting up to 2.8 gigawatts of energy by 2032.
And Google, too. Google signed an agreement with Kairos Power to develop what are known as SMRs, or Small Modular Reactors.
Now, that modular part is key, right? We aren't talking about those massive looming concrete domes from the 1970s.
Precisely. Modular means they aren't custom building a bespoke concrete cathedral on-site over 15 agonizing years.
Right, which always goes over budget anyway.
Always. Instead, they are manufacturing the reactor components in a central factory and just assembling them on-site. It's almost like industrial IKEA furniture.
Nuclear IKEA. I love that.
Yeah. It drastically reduces construction time and financial risk. It represents a massive pivot in corporate sustainability. They are moving from buying intermittent renewable energy credits to directly funding baseload carbon-free nuclear generation.
Okay, so they secure the power, they buy a nuclear plant, or they fund an SMR factory. Problem solved, right? We all go home.
Not exactly.
Right, because the sources reveal a massive roadblock here. If you try to take this shiny new private nuclear power and connect it to the public grid to balance your loads, you run headfirst into a brick wall of public resistance and federal regulation.
And this brings us to the third pillar, which features a really critical cautionary tale involving Amazon.
Yeah, walk us through the Amazon deal.
So Amazon struck a $650 million deal with Talon Energy to buy a data center campus right next to the Susquehanna nuclear plant in Pennsylvania. The plan was to operate, quote, behind the meter.
Behind the meter. Let's define that term for a second. Normally, a power plant sends energy out through the public grid, and your home meter spins as you pull it off the grid.
Right, that's standard.
But operating behind the meter means you build your facility physically on the power plant's actual property. You pull the energy directly from the reactor before it ever even hits the public transmission lines.
Exactly. But the Federal Energy Regulatory Commission, FRC, actually stepped in and paused the effort to increase the power flowing behind the meter to Amazon's site.
Wow. Why would they stop it if it's on private property?
The mechanism behind FRC's decision is super fascinating. Their core concern was grid stability and fairness.
Okay.
Even if a data center is primarily running behind the meter, it is still physically tethered to the broader public grid as a backup.
Ah.
Right. So if the nuclear reactor trips off for routine maintenance, that massive data center instantly pulls its power from the public wires just to stay alive.
Because of the 5 nines, they can't ever go down.
Exactly. So regulators argued that Amazon was getting the benefit of a highly stable public transmission system as a backup without actually paying its fair share for the upkeep of those transmission lines.
So the fear is that this shifts massive infrastructure costs onto regular utility customers. If the grid has to be beefed up just in case Amazon needs it, everyday people pay for that beefing up.
Exactly. And that triggers intense political friction.
Which makes total sense. And I want to be incredibly clear with you listening right now. We are not taking a side on this political debate.
No, absolutely not.
We are not endorsing the views of the politicians, nor are we endorsing the tech companies. We are strictly examining the political friction detailed in our source material because this exact pressure is actively forcing big tech to completely change its engineering strategy.
Right. And you can see why. U.S. senators have literally launched formal probes investigating whether the massive energy consumption of companies like Google, Meta, and Microsoft is actively driving up residential electricity bills.
Because local constituents are furious about the prospect of tech billionaires artificially inflating local power markets.
Exactly. So put yourself in the shoes of a tech CEO right now. You can't wait a decade for standard grid connections. But if you try to share the grid using your own private nuclear plants, the federal government blocks you over transmission costs, and senators launch investigations into consumer price gouging.
You're trapped.
You only have one move left on the board. You should just cut the cord completely.
It's island mode.
Island mode. It sounds like a survival strategy, honestly.
Functionally, it kind of is. The INL playbook details what they call option 3 and 4 configurations, where a nuclear-powered data center is entirely physically severed from the broader public transmission grid.
No wires at all connecting it to the local town.
None. By physically separating the infrastructure, tech companies instantly bypass FURC regulations regarding transmission lines.
Because they aren't using them.
Right. They avoid public resistance over residential rate hikes because they aren't touching the public supply, and they dramatically speed up their own permitting processes.
It is brilliant from a bureaucratic standpoint.
It is, but I have to stop you there and push back on this a bit, because if we think about the broader societal implications, is it actually a good thing if our wealthiest companies just take their ball and go home?
That is the big question.
Right. If they completely separate their cutting-edge infrastructure and infinite budgets from the public grid, how does the local community benefit at all? I'm looking at the INL playbook, and it claims these sites generate $1.6 billion in annual value added.
Yes, that's what the data says.
But if the campus is completely isolated from the town, how does the town see a dime of that? Are we just talking about temporary construction jobs to pour the concrete and then they leave?
It is a highly valid skepticism, and it's one that city councils are actively grappling with right now. But the socioeconomic data in the INL report actually looks beyond the construction phase. It looks to the 20 to 30-year lifespan of these sites.
Okay, walk me through that. What is the community benefit if it's not shared electricity?
The benefit mechanism isn't shared electricity, it is shared tax revenue.
Ah, property taxes.
Exactly. A combined advanced nuclear and data center campus is a multi-billion-dollar real estate asset.
Hmm.
It generates massive, ongoing property taxes for local municipalities.
Okay, that makes sense.
Plus, it requires hundreds of highly specialized, high-paying operational jobs. You need nuclear engineers, security personnel, specialized IT technicians, and those people live in the community, buy houses, go to restaurants.
And I imagine they sign long-term contracts with local vendors for supplies and maintenance, too.
Exactly. From a municipal standpoint, you're basically dropping a massive commercial taxpayer right into your jurisdiction that requires absolutely zero municipal power or grid upgrades.
Wow. It's just a self-contained economic engine. They can fund the local schools without dimming the local streetlights.
That is the pitch, yeah.
Yeah,
But going into island mode doesn't just solve regulatory headaches and political gridlock.
there's more.
Oh, there is a massive engineering bonus. By physically containing everything on one isolated campus, engineers realized they could solve the single biggest physical problem facing artificial intelligence hardware:
Which is the heat.
the heat.
And this brings us to the fourth pillar, and honestly, the most brilliant engineering concept in our entire stack of sources: direct thermal integration.
It's so cool. Let's break this down.
Yeah. We really have to understand that a massive portion of a data center's energy doesn't even go to the processors running the AI math. You have tens of thousands of servers packed into a warehouse running constantly. They generate an unbelievable amount of heat.
Right, if you don't aggressively cool them, the silicon literally melts.
Just turns to slag. Traditionally, data centers use these massive, electrically driven air conditioning chillers.
Which consumes up to 40% of their total electrical supply. 40%.
Yeah.
Just blowing cold air.
That is a massive waste of electricity.
But when you place a nuclear reactor in a data center on the exact same isolated island grid, you unlock this really unique physical opportunity. Nuclear reactors at their core are just machines that generate incredible amounts of thermal energy.
Right.
Heat. Typically, we use that heat to boil water, create steam, and spin a turbine to generate electricity.
Okay, let me see if I'm picturing this right. Normally, the reactor makes heat, the heat makes steam, the steam spins a turbine to make electricity, and then we send that electricity into the data center to run a giant air conditioning unit.
Right. That's the normal, very inefficient way.
So you're saying direct thermal integration just chops out all the middlemen. It's almost like using the raw heat from your car's engine to directly power the air conditioning system, which frees up all the electrical battery power to actually drive the car faster.
That is the perfect way to visualize it. They use a technology called high-efficiency absorption chillers. Instead of using electricity to run an AC compressor, these chillers use the raw, boiling heat directly from the nuclear reactor.
Wait, hold on. They are using boiling heat to cool the servers.
Yes, it sounds completely counterintuitive, but it's basic thermodynamics. They use the reactor heat to boil a liquid refrigerant, usually water out of a salt solution, like lithium bromide.
Okay, boiling the water out of the salt.
Right. And boiling that refrigerant creates a massive pressure change inside the closed system. It effectively creates a freezing vacuum that chills the water circulating through the data center's cooling pipes.
That is wild. You are literally using the reactor's boiling thermal exhaust to create a freezing vacuum, bypassing the electrical conversion entirely.
Exactly. And this is the holy grail for hyperscalers. Because every megawatt of electricity you don't spend running traditional air conditioners is a megawatt you can pump directly into the AI servers.
So it fundamentally transforms the energy profile and the economics of the whole campus.
It really does. When a tech company is spending billions to build an island-moded facility,
Yeah.
maximizing the amount of electricity that goes strictly toward revenue-generating AI computation is everything.
Right, you want every penny going to the AI.
Yes. Direct thermal integration makes the return on investment for these highly expensive, first-of-a-kind advanced reactors actually pencil out. They squeeze every drop of utility out of the atom, the electricity runs the chips, and the exhaust heat cools them down.
Man, the elegance of that engineering is just incredible. Let's take a step back, though, and connect the entire journey we've just been on. Because the cascade of cause and effect here is wild.
It's a domino effect.
Truly. We started with a timeline crisis. Hyperscalers needing power in 2 years, colliding with utility grids that take 10 years to upgrade.
Right, and that timeline mismatch forced the tech giants to seek their own primary power sources.
And because AI demands flawless, 99.999% continuous operation, intermittent renewables like solar and wind just weren't enough. They needed the uninterrupted baseload stability that only nuclear energy can provide at a zero carbon scale.
But then, attempting to connect those massive private nuclear sites to the public grid brought on federal regulations from FERC, metering disputes, and intense political scrutiny.
Which pushed them into the ultimate endgame we see today, severing the cord. Building private, island-moded nuclear campuses that bypass public resistance, stabilize local tax bases, and utilize ingenious direct thermal integration to maximize their computing power.
It really is a complete structural reimagining of industrial power architecture.
Yeah.
And it's driven entirely by the unprecedented physical demands of artificial intelligence.
It is a modern gold rush, but instead of pickaxes, they're using small modular reactors.
Exactly.
And it leaves us with a final, somewhat provocative thought for you to mull over as you go about your day. We are watching the world's most powerful companies throw limitless capital at commercializing advanced nuclear technologies and even fusion power for their private AI data centers.
Which is amazing innovation.
It is. But if they succeed, if they actually crack the code on cheap, abundant, advanced nuclear power, well, that technology eventually trickled down to benefit the public grid and everyday consumer.
Or
Right. Or are we witnessing the permanent dawn of a bifurcated world where the digital realm runs on private, futuristic nuclear islands while the rest of us remain tethered to an aging traditional grid?
I mean, that is the defining infrastructure question of the next decade.
It really is. Well, thank you for joining us on this deep dive into the sources. Keep asking the big questions, keep looking past the invisible cloud, and remember, sometimes the most cutting-edge digital technology requires the heaviest, most physical infrastructure on Earth. We'll catch you next time.